Yeah, sure, I'm ready. I don't hear anything anymore. Is anyone saying something?
No, I think everyone's muted.
Okay, just quiet. Okay.
I'm not sure. I don't know who's supposed to be chairing.
Yeah. Okay, now you can hear us, right?
Yes,
Yes.
I can hear you. Oh, okay.
Okay, very good. So this is a joint talk between the Global Poisson Seminar and the conference we are having this week at Lydia Brulé. And I'm going to take this chance to thank Swiss Map for providing us with such great conditions. And I'm going to thank also Kai Behrend for giving this talk. So he's going to tell us about Lagrangian intersections in the algebraic case, I believe. But
Yeah,
right.
okay, so
Go ahead.
thank you. So my slides, I just stuck them in the chat. So you can have a look at you can follow along so that when the stuff vanishes from my screen, that you can still have a look at it. Okay, so I wanted to talk about well, Lagrangian intersections, the holomorphic case. And yeah, I should apologize to all the experts. There's not really much or anything new in this talk. So if you've seen me talk about this kind of thing before, you probably know already what I'm going to say. And yeah, anyway, and I'll start out, yeah, very slowly. So let me start out here. So, S is always going to be my complex symplectic manifold. OS is a structure sheaf, and of course we have a symplectic form, so that I'll call sigma, a 2 form, and it is closed. That's a symplectic form, and it induces an isomorphism because it's not degenerate between the tangent bundle on S, which I'll denote like this, and the cotangent bundle omega S by contraction. And of course, everyone knows that this induces a Poisson bracket on the structure sheaf, which is an antisymmetric biderivation and satisfies the Jacobi. And here's also, if you've never seen this before, this is how you can define it by inverting the symplectic structure. And of course, well, one of the main basic facts about this situation is that locally you can find Darboux coordinates, so I'll call them like xi and pi, I from 1 to n, so the dimension of S is 2n, and so in Darboux coordinates, the symplectic form looks like this: dxi wedge dpi, sum over I. And so, I get these, this is how the correspondence between vector fields and one forms goes concretely in the Darboux coordinates. And here are the, here's all in terms of the Poisson bracket. And locally, so what's most important about the Darboux coordinates for me is going to be that they give so a one form lambda, so I'll call it lambda, such that d lambda is equal to sigma. So yes, and so in Darboux coordinates, I can choose lambda to be this. So summation pi dpi. So right. So this is the one form, and I make a vector field out of it, right? And so the vector field is parallel to where x is constant, and then p equals 0 is a Lagrangian submanifold, right? So this is what the manifold locally looks like. And so such a form, lambda, I call it the associated Liouville field or form, and often that Liouville field is all we need, not really the full Darboux coordinates. And what it does, one way to look at it, as I try to indicate there, turns S into the cotangent bundle of L. So L is the 0 locus of P or of lambda, so where the P's vanish. And lambda generates the scaling action of this vector bundle. And so L, this where the x, so sorry, where the pi vanish is of course an example of a Lagrangian submanifold. So let me recall in general what the definition is. A Lagrangian example of a Lagrangian. So L, a submanifold is Lagrangian if first of all it has dimension n, so half the dimension of S. And if I take the symplectic form and I restrict it to a 2 form on L, then it vanishes. So one way to think of that is if I draw here the tangent bundle to S and the cotangent bundle and its isomorphism given by contraction with the form, I restrict this to the Lagrangian, then this composition here vanishes. So that's the tangent bundle to the Lagrangian into the tangents of S, and then from the cotangent quotienting to omega L. That vanishes. So therefore, this map here actually maps to here. And so I get an isomorphism of the tangent bundle of L with the co-normal bundle of L, and an isomorphism of the normal bundle with the co-normal bundle, right? This is the normal sequence and the dual to the normal sequence of the submanifold. And so this is a basic fact about Lagrangians, that the tangent bundle is equal to the co-normal bundle. The normal bundle is the cotangent bundle. And another fact about Lagrangian submanifold is that you can always locally find Darboux coordinates such that L is given by the vanishing of the pi. Okay, so now let N be a second Lagrangian submanifold in S, and we're interested in the intersection. So that's X is always the intersection. S is the ambient symplectic, X is the intersection of L and N. That's the space I'm really interested in. And so let me start out by talking about intersection numbers briefly. So supposing this intersection is compact, then you can define the intersection number. So it's just like the virtual number of points of X is the number of intersection points. And how that is defined is, well, it's important, of course, that the dimensions of the two manifolds you're intersecting add up to the dimension of the ambient manifold. And so if you wiggle the two submanifolds L and N a little bit topologically, they will intersect in finitely many points transversely, and that's a well-defined number of X is compact, and that's the intersection number. And so, yeah, so if you wiggle L and N topological until they intersect in finitely many points, and then you count those points. That's this intersection number. But what's special about Lagrangian intersections is that you can meaningfully talk about the contribution of each point to this intersection number. So each point, P in X, each point of the intersection contributes to this number. That's something that usually doesn't make sense if you're intersecting manifolds in an ambient manifold, because it's all topological and it's defined in terms of wiggling. So let me explain that. So, so let's choose locally Darboux coordinates for L. So L is given by the vanishing of the pi, so that my symplectic manifold looks like the cotangent bundle of L. If I've chosen the Darboux form, generically, then this other submanifold N will also be transverse to this to the fiber of that bundle projection, and so I can think of this N as a section of this bundle over L. So it's then it's given by equations like Pi equals Fi of X. That's necessarily the way that it's going to be for submanifold transfers to these fibers. And so I plug this equation into replace Pi by Fi in the symplectic form. I get 0, and then I rewrite this like this. And so that says that this one form here, which is now a one form on L, because everything depends only on the x's, and the x's are coordinates on L. So it's a closed one form, d of it is 0. So locally, I can suppose I have an antiderivative. So the partials, so these Fi here are the partials of one function f. And so n is given as as the graph of this exact one form. So x is the intersection of Pi equals 0 and Pi equals these sum of the partials. So that is the same. It's just the partials of xi being equal to 0. So L, right? So x inside L. So if I think of the intersection x here, inside L, it's actually the 0 locus of the partial derivatives of this function f. So x is the critical locus of f, where a holomorphic function f from L to C. So this is, of course, I've gone through re-deriving. This is, of course, well-known fact that locally the intersection of two Lagrangians is the critical locus. Okay. So once we have this holomorphic function on a manifold, on a smooth manifold L, and I have a point in the critical locus of this function, I can define this following number. So I'm not going to explain all the terms here, but there's something called the Milnor fiber of f at the point P, and you compute its Euler characteristic, and then you make this. So 1 minus the Euler characteristic, and you change the sign, and that is this number mu of P. So this is like a Milnor number, generalized Milnor number of the function f at a critical point. And the fact is actually that that this number mu of P only depends on the singularity of the analytic space x at the point P. I'm intersecting these two Lagrangians. I'm mostly interested in the case where this intersection is really bad and really singular. So that's actually the most interesting case for me. And so it has lots of singularities, including lots of nilpotents in its structure sheaf, and just the structure of that singularity, the singularity determines this number mu of P. And then it's a fact that this intersection number of the two Lagrangians that I defined above is actually the weighted Euler characteristic with respect to this number. So the weighted Euler characteristic of this intersection weighted with respect to this number. And that's due to the I guess in the end, the microlocal index theorem, which is like due to McPherson and Kashiwara. It's some kind of generalization of the Gauss-Bonnet theorem to singular spaces. So this mu of P is the contribution, is what I call the contribution of the point to this count. So it's my goal in this story is to, so here I come to what my goal here in this talk, and in general, my goal in this situation, why I ever got interested in this subject to begin with, is to categorify these Lagrangian intersection numbers, i.e. defined a cohomology theory on the intersection such that this intersection number, this weighted Euler characteristic, is actual alternating sum of dimensions of some cohomology theory, so some coefficient system on X. So that's the coefficients, some kind of sheaf of coefficients or complex of coefficients on X. So, of course, the singularity theory gives us an answer to this question. If I have the critical locus of a holomorphic function, this critical set supports the perverse sheaf of vanishing cycles of F. And it's a fact that the perverse sheaf of vanishing cycles, if I restrict it to a point and then compute its fiber-wise Euler characteristic, I guess get this number mu that I introduced up here. So gluing together, if there was a way to glue together these locally defined perverse sheaves to a globally defined perverse sheaf capital Phi on the intersection on all of X, this will be one way to solve this problem of categorification. And well, one way I should point out in which this has been done in the meantime is so Joyce, Dominic Joyce and his school, students and postdocs, lots of people involved in this, he defines a notion of decritical locus, which I'm not going to get into here. I just want to mention this theory that there's a, so that's like, so a Lagrangian intersection is an example of a decritical locus. And if you further find an orientation on this decritical locus, then you can, that's exactly what you need to glue together these perverse sheaves. So then if you further find an orientation of this decritical locus, then this gluing works. And so this is one way to go about this. Of course, there's other other people have worked on this, and as I said, I'm okay. but so I don't want to go this route. So there's other things we can do, and so I want to start talking about by talking about the derived structure sheaf. So derived structure sheaf of this analytic space X. So what is that? So we have the structure sheaves of the two Lagrangians, OL and ON. OL and ON, these are, of course, sheaves of modules over OS, right? I extend them by 0 to S, and then they become OS modules. And I can form the derived tensor product. And that's an object in the derived category of OX modules. So, and it's actually in the bounded derived category with coherent cohomology. So that's a nice object in this derived category. But I want to be more concrete, so I want to explain to you what this actually looks like locally, this object in the derived category. So let me explain how to go about computing this, at least locally. So what we're going to do is we're going to resolve ON as an OS module. That's what you have to do to compute this kind of derived product. So resolve it by locally free OS modules. And so what we're going to do, we're going to choose well, now we want to resolve ON, so not OL. So this is N. And so I'm going to find a Liouville form that is parallel to this foliation, but its 0 locus is N. Right? I can always, I mean, in fact, here I can write it down for you. So, right, N was the graph of df, so in coordinates this looks like this. Right, pi are the coordinates on the fibers, and n is the zero locus of nu. I'll write it like this. I think of these fibers of this bundle projection as a foliation on a locally given foliation on the symplectic manifold, and I will call that F. So that's a Lagrangian foliation, and so it's a subbundle of TS, of the tangent bundle of S. But I again, because it's a Lagrangian foliation, I get like, you know, the dual of is the projection omega s to F dual, and this composition here is again 0, so I get that, right, F is actually isomorphic to its orthogonal complement with respect to the product given by omega. And that so the point is that this Lagrangian, sorry, this Liouville field that cuts out n is actually a section of right, because it's parallel to L, it's actually a section of F. So nu is it's a regular section of F, meaning it cuts out exactly n as a submanifold and gives me a resolution. So right, nu as a section of the bundle S defines dually a contraction map from F dual to OS. And then I can continue by taking exterior powers of the dual of this bundle, and I get the causal complex of nu. So that's the causal complex, and it resolves ON. And then, so now I've got this complex which resolves ON, and then tensoring with OL is actually just restricting to L. And so I just take this complex and restrict it to L, and it maps then to the structure of OX. It's not a resolution anymore of OX, though. But another point here is that TL now, so the tangents to L are transfers to the foliation F. So right, so TL maps into there. It transfers to F, so TL will map isomorphically to this guy here, which is F dual. So when I restrict to L, F dual turns into TL. And nu, you can see, turns into, right, so pi equals 0 turns nu into just simply df. And so, what I've proved for you or explained here is that locally this derived structure sheaf is given by this complex here. So it's the tangent bundle of the submanifold L, its exterior powers, and then contraction with this closed one form, df, or contraction with an exact one form. And right, this is now a complex of vector bundles on X, on the intersection. Its cohomology sheaves are known as the higher torsion sheaves. These are the cohomology sheaves. These are the higher structure sheaves of the intersections. These are sheaves of OX modules. So for right, so they're sitting. This is the degree 0, and it goes into negative degree. Okay, now what we notice something special here in this, you know, I could have done most of, you know, okay, that this df It's a derivation with respect to the Lee-Skelton bracket on the tangent, this Skelton algebra, basically, right? I have the bracket on the Lie bracket on TL extends to the Skelton bracket on this thing, and this df, because it's a closed one form, is a derivation with respect to that bracket. So the bracket passes to the cohomology, and so this makes this graded algebra Tor a sheaf of Gerstenhaber algebras on X. So that's like a Poisson algebra, but the bracket has degree +1. Right? If I take, because TL is in degree -1, if I have a bracket from TL and with TL back to TL, that's actually of degree +1. And so this is a theorem that I proved back in a paper with Fantechi, which was our contribution to the Manin festschrift. I think it was like 2009 or something like that. That these locally defined Gerstenhaber brackets that I constructed for you here, they glue to a globally defined Gerstenhaber structure on these Tor sheaves, which are of course globally defined canonically on S. And the proof that we came up with was it's a rather cumbersome gluing procedure, but okay, that's what it is. An example, let me just briefly mention the self-intersection. If the two Lagrangians are actually equal to each other, the intersection is of course then the Lagrangian L itself. You can see from, yep.
Is this Poisson structure on the intersection supposed to be non-degenerate?
Non-degenerate.
I ask this because they say that intersecting two zero Lagrangians should give you a -1 symplectic.
Yeah. No. Of course. Yes. I mean, I was going to briefly mention that too. Yeah. So this is yeah. I'm gonna. This comes in my just a little bit further in the slide. Just briefly, the self-intersection case. So if this, in the case of self-intersection, locally the function that the intersection is a critical locus of is a zero function. So I have no differential, and what I've got is simply so that these Tor sheaves are simply the higher exterior powers of the tangent bundle with the Skelton bracket. And I have a brief indication here that, so you can also think of the tangent bundle of L as I mod I squared, where I is the ideal sheaf, and you can directly get the Skelton bracket here from the Poisson bracket on S. So this, just in this simple case of the self-intersection, this thing proves for you that it's canonical and glues globally. But okay, that's maybe just a very I mean, it's just a self-intersection case. So I want to mention derived geometry briefly. So after this came after this stuff here. So so it was first Pantev, Tawenvaki, and Vitsozi who introduced this notion of symplectic structures in derived geometry, and also shifted symplectic structures. And so this derived category object here, which I've been talking about, is actually the structure sheaf of the derived intersection. So there is a derived scheme, or sorry, misprint. The derived intersection scheme, or analytic space. So that's its derived structure sheaf. And so first of all, this Lagrangian intersection is a -1 shifted symplectic structure. So it is non-degenerate in the derived sense. And then if you invert the symplectic structure, you get the Poisson structure, which then of degree +1. And so what I've explained here is how you locally get this, thing. So this bracket on these Tor sheaves is like the classical shadow of this derived Poisson scheme X. That's the way I think of it. What next? So the question that occurs is, can we find a matching to this Gerstenhaber bracket a BV operator? So one way to think of it is as it's a generator for the bracket on these Tor sheaves. To do this, we need like some orientation type stuff. So to do this, some bundles need to be, well, not trivialized. So what I say here is to do this in the least brutal way, what we need to choose is half densities on the two Lagrangians. So these are line bundles, which I'll call epsilon L and epsilon N, so the second, so if I tensor it with itself, I get the canonical bundle, the canonical line bundle, the highest exterior power of the cotangent bundle on L and N. And then, instead of considering the derived tensor product, we consider the derived harms, derived chief harm of these. These are still OS modules, epsilon N and epsilon L, and I consider these derived harms. Again, this is an object in the derived category. And to explain what's going on, that we look at it again locally. So, I mean, it's the we have to resolve this guy over OS. This time it's not the structure sheaf we're resolving, but the slight twist. So what I'm going to assume for simplicity is here that that there exists a line bundle epsilon on S, or at least in a neighborhood of X. So let's call it epsilon. Whose second exterior power is the highest exterior power of this Lagrangian foliation F. Why is that? Because, as I had already explained, the tangent bundle to F is the dual of F, so TL. So F, this foliation F, if I restrict it to the two Lagrangians, I get the cotangent bundles of N and L. So the highest exterior power of F restricts to omega NL and omega NN. So here was the resolution of the structure sheaf I had before. So now I just tensor it with this epsilon. So tensor it with epsilon. I still get a resolution, well, now of epsilon N. And then this R harm, because I've resolved this guy here, I have to take the dual of its resolution. So that's here. So I just copied down this thing here and put the dual, and then I have to restrict it to the other Lagrangian L and tensor with its omega L. Okay, so because I take the dual of the dual, the duals cancel out, and so and the whole sequence reverses, goes the other way around when I take duals, right? So this lambda, this epsilon turns into epsilon dual. This guy here turns into F tensor epsilon dual, and so on. Then, because I tensor with omega L, and so epsilon restricted to L becomes epsilon L. This epsilon cancels, and I get this thing here, and F turns into omega. And so what I see is that I get the sheaves in this in this complex are just the sheaves of forms on the Lagrangian submanifold L, and the differential is now multiplication by df. Right. So again, f is the function. Right, such that n is the graph of df on L. So the R-harm is this complex, and remember the L tensor was like, the Schouten algebra. Here it was contraction with df. Here it's multiplication with df. And so we see that this guy here, so that the Schouten complex acts on this one by contraction, right? Just contract the polyvector fields against a form to get another form. Right. So this guy acts on this one by contraction, and in fact, you can see that well, locally these. So if I have a trivialization of this bundle, these two actually become isomorphic. So in some sense, this R-harm is an invertible module over this thing, locally the same. So so if I take the cohomology of the R-harm, I get the X sheaves, and so I also get that these Tor sheaves act on the X sheaves in this way, and right, and so in fact Tor I acts on Xj I get to Xj minus I. Now I'm going to call this highest sheaf X here, this Xn OS epsilon n epsilon L epsilon X. So this is an invertible OX module, and so if that's the last cohomology object of this complex, right? And so it induces an isomorphism of the ith Tor sheaf with the n minus first X sheaf. So really, there's this R-harm with these epsilons is just locally the same as this derived structure sheaf, but not globally. And so this complex, of course, also has an extra structure. Right? There's the de-Rham differential, and the de-Rham differential, it commutes with the multiplication by df, well, because df is exact or closed. Right, so we have this. So the d passes to the cohomology. After I take the cohomology with respect to multiplication by df, I still have the de-Rham differential left there. So I get a differential on these X sheaves. And so again, this is something we proved in that Manin festschrift, but unfortunately we screwed up the signs terribly. And so the corrected version of our theorem there is that this d, this extra differential, which I just locally defined for you here from xj to xj plus 1, locally constructed as above, glues to a global, which we call BV operator, and I call it delta. So it exists globally. Right. These X sheaves, of course, exist before we start out doing anything, and so now we got this delta. And the proof is again some tricky gluing, and you have to, it's very easy to make sign errors when you glue there, because there's some canonical maps that apparently are multiplication by -1 and not the identity. So anyway, so this is the way to fix it. Right, and since there's a compatibility between the Schouten bracket and the de-Rham differential, this compatibility passes to cohomology with respect to df. And so I just wrote down what this means. So the compatibility with this bracket on Tor with this differential. So first of all, it could happen that this sheaf here is, if we were to be able to trivialize it, so that these Tors become isomorphic to the x, and then we can move the differential on the x over to a differential on the Tors. Right, then the Tor would be equal to the x, and we move the delta over there, and then we have this equation here, so that the delta is a generator for the bracket. In the general case, right, we have to involve sections of this invertible sheaf, and so they're called M, and so then this equation becomes this equation here. I tossed in this one here, which is 0. I mean, M is in the highest degree, so delta of it is automatically 0. But if I write it like this, it's clear that this delta is a second order differential operator on this X module whose symbol is the Poisson bracket. Sorry, the Schouten bracket. Right, yeah. So again, in the case of the self-intersection, where the Tor sheaves was just the Schouten algebra, the X sheaves are just the de-Rham. But again, then there's no wedging df. The cohomology sheaves are just the sheaves of differentials. And there's the de-Rham differential. So in the self-intersection case, this is just these X with their BV operator is just the de-Rham complex. So therefore, by generalizing that, we could think of this X sheaves X complex with its operator delta as a kind of generalized de-Rham complex or virtual de-Rham complex of the Lagrangian intersection. And this you might think of doing, but it turns out that that is maybe not the greatest thing to do, because the cohomology sheaves with respect to delta of this virtual de-Rham complex are not necessarily constructible. So there's counterexamples that I learned this from Duke van Straten, that there's actually counterexamples to this. I mean, this was I mean, it's natural to conjecture this because it's true in the self-intersection case, and there is also some paper that have claimed these kind of results, but they turn out to be wrong. So you can't really expect to categorify these numbers if you don't at least pointwise get anything finite out of this. So what you have to do is still work a little bit harder. So it's not good enough to just work with these higher structure sheaves, these X and the Tors. You have to work fully derived, is one way to think of it, I think. Let me say, so if we were lifting this operator delta to a BV operator on the full derived R HOM, right? That this complex that locally locally looks like this here, right? Over the full Gerstenhaber algebra, the derived Gerstenhaber algebra, this is what I would be considered by quantizing the shifted Poisson derived scheme. Right? There's this shifted Poisson derived scheme with a this is the derived structure sheaf, and lifting this delta to this, that would be quantizing the shifted derived. So of course, people have worked on this, and the derived geometry people have to, there's the same names as earlier, and lots of other names. There's too many to mention there. Yeah. Of course. Well, maybe I wanted to remark that there's yeah, there's a whole bunch of, this is a kind of going off on a tangent. There's a whole bunch of spectral sequences you can write down in this context, and there's, people have been interested in this, and so there's some recent results by Mladenov on the degeneration of the spectral sequences. Right, we've got a generalization of the de-Rham complex, so you can ask about like degeneration of analogs of Hodge to de-Rham spectral sequences and so on. And in certain cases, these do degenerate, but it seems to be so far restricted to smooth, compact, and Kähler intersection. So, and as I said, mostly I'm not so interested in the case where the intersection is smooth. Okay, so as I said, we need to work fully derived, and one way to do this, to solve this problem of extending this BV operator to this complex, not just to its cohomology sheaves, is quantization. So deformation quantization of the symplectic manifold. And so the slogan well, what I claim is that first and a little bit of second order deformation quantization is actually enough to achieve this. So I wanted to say this, there's a more more natural way to construct this delta on the X instead of gluing, and it's fully derived version. So, and of course, the full deformation quantization of OS has been studied by many people, and also the quantization of the Lagrangian submanifolds has been done by many people, and also the quantization. So I should, because I'm going to run out of time, mention now that of course in that so if you do this full deformation quantization, you do, and after you invert the full deformation quantization parameter, you get perverse sheaves. This has first been proved by Kashiwara and Shapira, and yeah, so that's one way to do it. And so you can, it's been known actually so for a long time. And so I'm not claiming much new here. I just, what I'm observing here is, what I'm maybe claiming is that you don't need to go all the way to the full quantization. And so this is what I call my slogan here. For purposes of this, what I'm proposing, these first and second order quantizations are actually enough. And some of the first and second order case are both easier and harder than the infinite order case in some sense. They're not just one follows from the others in the most simple way. So I wanted to explain some of the stuff. Okay, so now I'm just going to get a bit technical. So first of all, let me a few generalizations on what one thing that's very important in this context is divergence. So fundamental for this is the notion of divergence. So L is just, this works on any manifold on dimension n. So I just want to recall what is usually divergence. It means you choose a volume form, so a trivialization of the highest exterior power. So the top forms a volume form, and then so you look at the differential from the top, well, not the top forms, right? The top forms 1 n minus 1 forms to omega n is d. Here, by contracting with the volume form, you can map TL into omega n minus 1, and OL becomes omega n. And so you can, via these isomorphisms, you transport this de-Rham differential over to here, and you get what's known as divergence. So it uses to transport this D over to a divergence. But you can define if you have a half density on your manifold, you get a more natural notion of divergence, which doesn't depend on the choice of a volume form. And so here's the definition of it. So if you have a vector field in TL, and you have a section of the half density, you can define it like this. So the vector field acts on the half density by this formula. So m squared becomes a section of the highest exterior power. So I can contract that with the vector field, and then I'm up here. I applied the de-Rham differential to that. I get a top degree form, and if I divide that again by the section of the half density, I'm back in the half density. So that formula makes sense. It has some nice properties. So so if I have a function a on L, it's neither linear in the first argument nor linear in the second argument. But if you look at the second equation, for example, you see that if for a fixed vector field V, I get an operation on this epsilon. And because of this, how this commutes with multiplication by A, I can see that I have a first order differential operator with the symbol being 2 times V. So it splits this idea class sequence. The differential operators of order less than or equal to 1 of epsilon. It is a splitting of that, but of course it's not a linear splitting, so it doesn't define the connection on epsilon. And another thing I can do if I have a half density is I can talk about self-adjoint operators of order 2. So the definition is like this. So a differential operator of order 2 on epsilon is self-adjoint with a symbol zeta if it satisfies this definition here. So if I commute with multiplication by a scalar function, it's second order, so I get a first order operator, and that's this divergence operator. So that's what it is. So if I denote these self-adjoint operators by diff star, I get an exact sequence like this. So the symbol goes to S2TL, but now the kernel is only OL. So I've got like rid of the order 1 part, so to speak. So now I'm going to go back to the symplectic manifold S. And so what am I saying here? So there exists a canonical first order deformation quantization of the structure sheaf of of S. Here it is, OS plus epsilon OS. So epsilon squared is the square zero parameter. So it's just OS plus epsilon OS. And here's the multiplication. So I multiply this, the star denotes the multiplication. So this part is multiplied by epsilon. So modulo epsilon is just multiplication in OS. The next term, so if I just multiply two functions in S, A0 and B0, right, I get an additional term epsilon over 2 times the Poisson bracket A0 and B0, and then this term is just comes from these epsilon, this guy multiplying here and that guy multiplying there, where it's just function multiplication again. So it's a sheaf of C epsilon algebras on S. If I divide by epsilon, I get OS, an epimorphism of sheaves of algebras, and I have this equation here. So this is the commutator with respect to the star product. This is the Poisson bracket on OS, and this is true for all sections of A. And this is actually, of course, exactly the definition of a first order deformation quantization. So this first order quantization of the symplectic manifold is completely boring, but already the quantization of the Lagrangians is completely non-trivial. So a sheaf of A modules ML on S is called a quantization of this guy here. So first of all, right, if it's an A modulus, also epsilon acts on it, so I can divide by epsilon, and I get, because epsilon squared is 0, the quotient by epsilon maps by multiplication to epsilon back into the guy itself, and I require this to be an exact sequence. Moreover, if I reduce mod epsilon, of course, I'm supposed to get the epsilon L, because I'm quantizing epsilon L. So really, this short exact sequence, I can rewrite it like this. So it's an extension of epsilon L by itself, by some ML, which is an A module. And I'm going to single out certain kinds of quantizations called distinguished quantization. It's easier because, so they satisfy this equation here that A star M, if A is actually in the ideal I, so the ideal of inside OS of functions that vanish on L, right? So that A is a function in I, then it maps into I mod I squared, which is the tangent bundle on L. So I can turn A into a vector field on L, and then I can plug it into the divergence, and then it makes sense to require this formula here. So it's a little bit of an analog, like doing this requirement here. It said we also have a requirement like that up to epsilon, the axes are completely random. So theorem you prove is that these distinguished quantizations of epsilon L form a gerb over S, so on the side of open subsets of probably S, I don't know, it doesn't make a difference. They form an OL gerb, so let me tell you what that means. Well, quantizations exist locally. That's first of all what it means. And if I have any two, so ML and ML prime, then I have a sheaf of isomorphisms. This sheaf of isomorphisms has to be a principal homogeneous bundle for this sheaf of abelian groups OL with respect to addition. That's what it means to be an OL gerb. And maybe I'll just briefly, I'm running out of time and it's getting very technical. So I briefly should mention that to prove that these exist locally, you locally choose Liouville fields, which give you a splitting of this normal sequence of L and S. And then you can define an action of this trivial thing on this trivial thing by this formula here. So locally, these guys always exist because you can use Liouville fields to define them. And then the thing is that if you have another Liouville field, so you have the one defined by one Liouville field and the one by the other, the isomorphisms is given by these self-adjoint differential operators. That's why I mentioned them. And so if I have a self-adjoint differential operator on epsilon, the corresponding isomorphism is given like this: identity plus epsilon times psi. So it goes like, it goes like backwards like that, or backwards like that. And so the normal sequence for L is self-dual. So if I think of it as an extension, it defines a class in H1. It actually defines a class in H1 of the second symmetric power of TL. And so if I look at this short exact sequence of the second order differential operators, the normal sequence for L gives me a first degree cohomology class here. And so the boundary of this sequence gives me a second order cohomology class here. And so what I'm claiming is here that that's how I get the class of this gerb in H2 of L. So this is the cohomology class of this gerb of quantization of epsilon L. And okay, so that's just to explain concretely what this gerb of first order quantizations of epsilon L is. Now, if I assume that both epsilon L and epsilon N have been quantized, then I can consider this short exact sequence of complexes. So here's R hom over A of the quantizations. If I mod out by epsilon, I get the R hom that just classical R hom, so non-quantum R hom. Right, so I get an extension of this guy by itself, which I can think of as a map of degree 1. And my claim is that that degree 1 map, when I pass the cohomology, reproduces our BV operator on cohomology. So if I have these quantizations of the Lagrangian submanifolds, I can solve my problem. And so then you have to argue with the gerbs. And the main problem here is that you have one gerb obstructing the quantization of epsilon N, another one obstructing the quantization of L. And the problem is, are these on the intersection, do they give the same gerb? Otherwise, you're stuck because your things are twisted. And so that's the hard part. And so for that, you have to go to the second order quantizations of OS. And so that gets more technical. So I'm going to skip all that because I'm running out of time. So I just want, so that just to say that in words again. So I have these obstruction classes, right? This H2 LOL, which I concretely described here, constructed on L. I need to prove that the one for L and for N restrict to the same on X. I can do that by extending them both into S. And that is done by looking at second order deformation quantizations of S and the obstructions to those are exactly what I need, and then the theory of twisted sheaves will solve the problem. So sorry about, I'm just going to skip all that. So and I was going to end here with this, right, once I have this PV operator on the derived harms, I construct a complex over this field where I join a formal parameter to the complex numbers. And I join the formal parameter to this guy here and look at this differential. So the internal differential plus u times delta. And that's the theorem that this is a perverse sheaf which achieves the quantization. And this is, as I said, due to Kashiwara and Shapira, I'm very confident that this thing constructed this way using only first, second order quantizations is going to be the same as they construct doing the whole thing. And it's also locally isomorphic to the sheaf of vanishing cycles, which has been proved by Sabah. Again, isomorphic, or maybe isomorphic up to some things I'm not 100% sure. Anyway, I want to finish with that. So, yeah, thanks.
Thank you.
Oh, there's a
question already.
question in the chat. How does this notion of distinguished contemporary to the works of Paul de Solution? Shapira. I thought the latter work provides a full formal quantization of upsilon L. So no, there are how do I say this? So there are obstructions to quantizing upsilon L. It depends a bit on your quantizations of the symplectic manifold S. So there is apparently a notion of canonical quantization. So there is so you can classify the quantizations of the symplectic manifold. There's something called a non-commutative period map, and it every such quantization defines all these obstruction classes. Sorry, if you have a quantization of OS, it defines a whole sequence of second cohomology classes in S. If all these sequences vanishes, you call this a canonical quantization, and apparently this and if it's canonical, this quantization, then actually all these obstructions to quantizing the Lagrangians vanish. And apparently that's what this sheaf of microlocal differential operators that Kashiwara and Shapira and this whole school use to quantize is canonical. So these obstructions vanish. I think that's how I should say it.
But would you say your quantization is something different from the sheaf of WKB differential operators?
So how do I say it? Well, I mean, you can tell this, I'm not, what am I saying? So, I think, well, like the way I see it is, I mean, the way I think of it is, so I look at, so there's a notion of, well, since you're asking the question, so, so where is, so, second order deformation quantizations. Okay, so briefly, you know, these second order deformation quantizations just, I mean, they exist locally. They're locally isomorphic. They form a gerb. So I pass to this gerb. Now I have a second order deformation quantization. Up there, I can I can now construct, I can pass to the further gerb that allows me to quantize the Lagrangian submanifolds. Since I'm doing R-Hom from upsilon L to upsilon M, that gerb cancels out and I'm back down to the gerb of second order deformation quantizations. And I have to work with the one way to, the language to use is algebraic, which is of course the same language that Shapira, Kashiwara, and collaborators, what they have to work with as well.
May I have a comment on this?
Yeah. Yes, please do.
In fact, thank you for quoting Kashiwara and Shapira, but the first who did it is Kashiwara in '96, but not in the symplectic case, in the contact case, not homogeneous. Yeah. For or if you want a symplectic, homogeneous symplectic manifold for conic Lagrangian. But he just wrote in one word that there exists a quantization once you twist by half densities, and then we prove the fact that when you have two quantization, Rm is perverse, and then Joyce asked me, that's good, you have perverse shift, but over the field CH bar, Florent series over C. So what about a quantization over field? And he developed his theory, which is of gluing things which are locally vanishing cycle, and it was very, very difficult, and it's another subject. So I don't know, you work over C or CH bar, no? What about other fields?
Well, all I know what to do to get a perverse sheaf out of this R-Hom with its extra differential is you have to turn this one complex with two differentials into a double complex by introducing this formal parameter. I don't know. I guess you have to invert that formal parameter to get a perverse sheaf. Yeah, I don't know what else to say to that.
So let's see, are there other questions? Oh, sorry, there's a question in the chat again, sorry.
Yeah, what's the advantage? Well, I don't know if advantage, the fully derived approach comparing with the vanishing cycles approach. I mean, I must admit, if someone here knows the answer to this thing that has been bothering me for a while, if I the only reference I know that compares this this perverse sheaf coming out of deformation quantization, right? This one here. With vanishing cycles is this work of Sabah on, so locally, this thing is the twisted de-Rham complex, right? As I tried to explain. Locally, this is just the twisted de-Rham complex. And so Sabah proves that this is related to vanishing cycles, but I don't know, I'm not, I mean, I don't know enough about D models to understand his paper. And when I read this paper, he only seems to prove that the cohomology sheaves are isomorphic. I don't know if there's if someone can tell me whether these are actually isomorphic. So if you take the actual perverse sheaf of vanishing cycles, you adjoin the formal parameter U, and then you also look at this perverse sheaf. Are they actually isomorphic as perverse sheaves over this field? Or do they just both give the same? I mean, do they both give the same Euler characteristic? I mean, are the cohomology sheaves isomorphic? And that's when I look at the theorem. So I don't know. There might be, and if the answer to that question is no, then you might actually get something slightly different globally. And I don't know. And this is more like my point of view. Even if it gives you the same answer, this is sort of a de-Rham point of view. Instead of like I mean, if you look at classically at cohomology, you can just look at cohomology of the constant sheaf C, and or you can look at de-Rham cohomology, and de-Rham cohomology have maybe more techniques. I don't know. That's just a very vague thing. I don't know. Yeah.
Right. Other questions? Maybe I can ask a very naive question. If you have a holomorphic symplectic groupoid and you start looking at the Lagrangian bisections, can you get any interesting information about their self-intersections?
Sorry, say again. I didn't hear the beginning of.
So you have a holomorphic symplectic groupoid, and you can look at their Lagrangian bisections. Is there something interesting going on that you could say about the corresponding Poisson isomorphism out of the intersection?
No, I'm sorry, I don't know.
Okay. Oh, there's another question from the audience. Marco, okay.
Can I ask, so it's just about the logic of the quantization idea. So you wanted to categorify this numerical invariant. So you quantized the intersection, and you associated a family of cohomology theories parametrized by U, if I understand correctly. And so what's the final, on your final slide, this idea that it's a perverse sheaf, presumably you want to show that it's independent of the quantization, or what? What's the logic?
Well, in the end, I'm extending my base field from C to this C adjoined U. And make the base change over that field, and that's then just my ground field. So
what is the categorification supposed to be? Is it supposed to be this cohomology at U equals 0?
So now X, my intersection scheme is now actually a scheme over this C adjoined U, over this field, and I have a a perverse sheaf on this space over that field. And if I have a point, well, the fiber-wise, Euler characteristic reproduces this generalized Milnor number.
So does it follow that you are able to categorify it only in the quantum region, but not in the classical limit? And is that the idea somehow?
Well, I haven't thought about this too much. I guess you can use that Joyce and his collaborators' approach to construct a perverse sheaf downstairs without the parameter U, and just formally base change by adjoining this U, and then you get what I've constructed here, or what Kashiwara and Shapiro were the first to have constructed.
Okay, thanks.
I don't know if there's a way to prove directly in this context that this thing descends. I mean, in Sabah's paper, yeah, he does prove that the usual sheaf of vanishing cycles, which doesn't have the parameter U in it, after you base change to this bigger field, it becomes isomorphic. At least their cohomology sheaves isomorphic to this guy here. So maybe it descends, but I haven't thought about it too much to try to prove this, in some sense, to prove that it descends without eliminating this U parameter.
Okay, so I don't think there are any additional questions. So thank you very much. Let's thank Kai again. So for the crowd at Global Poisson, goodbye. The workshop will have its last day tomorrow morning. So hope to see people there. Thank you.
Thank you.